Hi, we're going to do a proof. So we're told that if x over a is equal to y over b and that's equal to z over c, we're going to prove that this equation is true. Let's just go ahead and jump into it right away. Proof. So by assumption, we have that all of these fractions are equal. So we should give them a name. So let's say that we call them k. So it's k equal to x over a, which is the same thing as y over b, which is the same thing as z over c. So now we want to manipulate this left-hand side to make it look like this. So what I'm going to do is I'm basically going to solve for x, y, and z from this equation. So then, since k is equal to x over a, you can multiply by a to solve for x. So x is equal to, just multiply by a on both sides, and you get ak. Likewise, y will be equal to bk by multiplying by b, and z will be equal to ck by multiplying by c. And let's just focus on one of these. Let's focus on this one. So note, x squared plus a squared over x plus a. Well, x is ak, so this is going to be a squared k squared plus a squared over, and then x is ak, so this is ak plus a. So now what you can do is you can pull out an a squared in the numerator and an a in the denominator. So this is a squared k plus 1 over, and then here we have a k plus 1. That's a k squared plus 1. So this is equal to a k squared plus 1 over k plus 1. And so we can do the same thing with this one, right? We can do the same thing. I'll do one more. You'll notice that it's the same y squared plus b squared over y plus b. So y is equal to bk. So this will be b squared k squared plus b squared over bk plus b. Right? You're just squaring each piece. So when you square the y, you square the b, you square the k. That's how you got. That's how I got b squared and k squared. Then you can pull out a b squared. So you get k squared plus 1. And then you can pull out a b on the bottom. So you get k plus 1. So that's equal to b, because you cancel a b, k squared plus 1, k plus 1. So you can see, using similar reasoning, z squared plus c squared over z plus c. That's going to be equal to the same thing, except it's going to be c, right? So it should be c k squared plus 1, k plus 1. Okay, so now we're going to go ahead and write this down, and then we have to show it's equal to this. So I'm going to write it again down here. So then we have, I'm going to go ahead and write it here, x squared plus a squared over x plus a plus y squared plus b squared over y plus b plus z squared plus c squared over z plus c. It's pretty cool. It's just like an algebra problem. It's just really random and just kind of fun to play with. And then it should be equal to all of this. So we need to get somehow x plus y plus z squared, a plus b plus c quantity squared, and that on the bottom. So let's go ahead and start by just replacing this with what we have. So this is equal to, I'm going to write it below here. So the first one is a k squared plus 1, k plus 1. So it'll be a k squared plus 1, k plus 1, plus the next one is b. So b k squared plus 1, k plus 1. And the next one will be c, k squared plus 1, k plus 1. Looks like we can factor out a k squared plus 1. So we can do k squared plus 1 times a plus b plus c over k plus 1. Okay, so we need to get this, right? X plus y plus z quantity squared, a plus b plus c squared. So we need two terms, so because there's a plus here, and here we have one term. So let's go ahead and break it up as follows. This is equal to k squared a plus b plus c, plus, and then 1 times that will be a plus b plus c over k plus 1. So now we have 2 terms in the numerator, 2 terms in the denominator. And over here, same thing, right? We have 2 terms in the numerator, 2 terms in the denominator. So we need an a plus b plus c squared. So let's go ahead and multiply this by a plus b plus c over a plus b plus c to create that, okay? When we do that, we're going to get k squared, a plus b plus c squared, right? Because we're going to distribute this into this, plus a plus b plus c squared over, and then here we're going to get k, a plus b plus c, plus, and then a plus b plus c. So this is very similar to what we have. We're almost there, right? So we've got this, we've got this. We just need the x's. So remember that x is equal to ak, y is equal to bk, and z is equal to ck. So we can combine these. These are both squared, so you can bring the k in like this. Watch. This is actually ka plus kb plus kc squared. Properties of exponents, right? You can basically, there's a step I skipped, but basically you can take this and show this step, k, a plus b plus c, which I skipped, squared, right? So that's the same as that, okay? Because see, it's k squared, boom. A plus b plus c squared, boom. See, this is the same as this. And then you multiply the k through and you get that. Plus a plus b plus c squared over, same thing here, ka, kb, kc, ka plus kb plus kc plus a plus b plus c. And then ka, we know that's x, you see. Ka is x, kb is y, kc is z. So we have x plus y plus z squared plus a plus b plus c squared over x plus y plus z plus a plus b plus c. And that completes the proof. That's exactly what we had to show, right? That's what we had to prove in this problem. And this is an example in a book, an old book. I have it here. This is the book, in case you're curious. I'll leave a link in the description in case you want to check it out. It's kind of fun. And it's called Higher Algebra. It's by Hall and Knight. It's a really old, just give it a whiff. Nice old book. And it's got really hard examples and really interesting problems. Hard examples, harder problems. It's all algebra, right? It's just like basic algebra, but it's a higher algebra. And this book was published in the 1800s. So kind of fun. I hope this video has been helpful. Good luck.